Hey all, so we're going to keep going with our discussion of integrals, and we're going to do some review with our lovely definite integrals today. And so you have 5.2 and 5.3 homework with your presentation in 5.3. As a reminder, I only want you doing 30 to 45 minutes of math each day. When I split it up, I do recommend that you do a little bit from each, though I don't expect you to do every single problem. Now, for some of these integrals, you're going to want to do a quick review of the definite integrals. A lot of these are going to be, they'll come back fairly quickly if you remember your rules for the derivative. But let's review a couple, especially these polynomial rules. So for number 1, we have 3x minus 9. And I would have you remember that the integral of x to the n dx is equal to 1 over n plus 1 times x to the n plus 1. And if we have a constant, that integral is kx. Hopefully this feels pretty familiar. So the first thing we want to do is we want to take the integral of 3x minus 9, and then we'll worry about these bounds on the integral. So 3x minus 9, we can separate the terms, and we end up with the integral of 3x. Using our polynomial rule becomes 3 times 1/2 x squared, increasing the degree there, minus 9x, using our constant rule, with the bounds from 0 to 10. Now, the next thing, and this is coming into the fundamental theorem of calculus, as you see our topic is right here, states that if you have a definite integral from a to b, then that's the same as that is equal to the value of the integral at b minus the integral at a. Hopefully you remember that the antiderivative of f we represent with a capital. So in this case, that would be 3 over 2 10 squared minus 9 times 10, which would be f of 10, minus 3 over 2 0 squared minus 9 times 0 for the lower bound. And we're going to end up with 60 minus 0, which is just 60, as the value of this definite integral. I would also love to remind you that for all definite integrals, you can also use your calculator. So we had a couple questions about using your calculator for the derivative on earlier lessons. So I just want to make sure we go over how to use your calculator to find an integral. Now, for most of you using a TI, you're going to go to Math and then scroll down and go to fn int. It should be right next to your derivative function. And some of you will be able to then type your integral in just like this. And that's going to be great. Some of you have an older device, so I do want to go over that. If you have an older device, it will just say, okay, here's your function, tell us what to do. And you want to type in the formula. So in this case, it would look like that. Then you put a comma and the variable again, so that it knows this is like the equivalent of the dx. What variable are we using? And then the bounds, all separated by commas, and close the parentheses. So that's how you would type this in if your calculator doesn't let you write like that. And the answer you get is 2,671.5. Of course, we could do this one by hand, but again, after seeing the results about calculators and derivatives, I definitely wanted to go over it. So there are some more complicated problems that we can solve with the fundamental theorem of calculus. The fundamental theorem of calculus has two parts, and what it says is that if f is continuous on a to b, then the function antiderivative of f is defined as the integral from a constant to x of f of t dt. And it's continuous on a to b and differentiable on a to b, and the derivative of x is f. So this is basically the idea of the antiderivative right here. The other important thing we've gone over already is that the integral from a to b of f of x is antiderivative at b minus antiderivative of a. Now this can be really helpful because here we have the derivative of the integral of 0 to x squared. We've got all this going on. So let's talk about how we can use the fundamental theorem of calculus to solve this problem. Now we're going to start off by starting with this first step here. We're going to say, well, f of x would equal, we're still going to use 0, that's fine, to x of root 1 minus t squared dt. But we don't have x. We have x squared. So we're just going to change the same thing on both sides, just like we would for a normal function. F of x squared is equal to the integral from 0 to x squared of 1 minus t squared dt. So then the integral, we know this, is f of x squared minus f of 0. This is using our second part here. Now, what we want to do is take the derivative of this subtraction problem because we're taking the derivative of that integral. So the first thing we want to do is we can use the chain rule. So f prime of x squared times 2x, and we then say minus 0 because f of 0 is a constant, which means f of 0 is a constant, and so its derivative is 0. Here, we're going to use our final part of our fundamental theorem that says that f prime is the original function. So our original function right here, meaning that we have root 1 minus x squared squared, since we're plugging x squared in for t, times 2x minus 0, leaving us with our final answer for this problem of 2x times root 1 minus x to the 4th. Now, one thing you might have noticed is that 1 minus t squared is definitely not a nice, easy polynomial to solve, and because it's definite, you don't necessarily have to do this by hand. You might get a calculator, but you might not. Please be careful to pay attention to those different rules when you're taking your check-ins and your quizzes. But I will say, if you look at this on a graph, it might give you some good hints about what this looks like. Because if you graph y equals root 1 minus, and you'd have to use x squared, you end up with a picture like this. And what I would hope that you would realize is, oh, I recognize this. This is half of a circle, because if we solve this equation right here that we typed into our calculator, this becomes y squared is equal to 1 minus x squared. That's equivalent. Add the x squared over, and we have our formula for a circle centered at the origin. Now, since the integral is the area under the curve, that's just asking for your area here from 0 to 1 using the bounds. So we're just looking at 1/4 of pi r squared, the area of a circle. Which is why it's sometimes nice not to just immediately rely on a calculator or something like this, because we now see that the area under the curve here is pi over 4. Let me know if you have any questions about anything with the fundamental theorem of calculus or definite integrals, and I'll talk to you later.